This is third numerical on shear stress distribution. A simply supported beam carries a uniformly distributed load of 30 kN per meter over the entire length of 1 meter. The cross section of a beam is a T section with its top flange of 125 by 25 mm and wave 175 by 25 mm. Obtain the maximum shear stress and plot maximum shear plot shear stress distribution. So this is simply supported beam of length 1 meter with uniformly distributed load of 30 kN per meter, and cross section of this beam is this T section with flange width 125 mm, flange thickness 25 mm, this wave thickness 25 mm and wave depth 175 mm. First step is to find position of neutral axis. Y bar is equal to, let us consider this wave portion as 1 and this flange portion as 2. Y bar is equal to A1. A1 is area for that wave portion, because we consider this wave portion as 1. So A1 is area for that wave portion. Y1 is centroidal distance for only for that wave portion from that lowest outermost fiber to centroidal distance only for that wave portion is this Y1, plus A2 is area for that flange portion and Y2 is centroidal distance for that flange portion from bottom fiber. Bottom fiber, that means this bottom fiber. This is bottom fiber. This yellow portion is bottom fiber upon A1 plus A2. Now this A1 is 175 multiplied by 25, 4375 mm square. Y1 is 175 divided by 2, 87.5 mm. A2 125 multiplied by 25, 3125 mm square. And Y2 is 175 plus 25 by 2, 187.5 mm. Therefore, this Y bar is equal to 4375 multiplied by 87.5 plus 3125 multiplied by 187.5 divided by 4375 plus 187 plus 3125 is 129.17 mm. This Y bar is the centroidal distance for the T section, and distance for that centroidal distance from bottommost fiber is this 129.17 mm. Next step is to find moment of inertia. moment of inertia I is equal to I x1 I x1 is moment of inertia for that wave portion plus I x2 is moment of inertia for that flange portion. I is equal to so we find this neutral axis is at a distance 129.17 mm from bottom fiber. That means from this bottom fiber to this neutral axis distance, this distance is 129.17 mm, and only for that wave portion neutral axis is 87.5 mm. That means here, this red line is neutral axis only for that wave portion. $87.5. This is half of 175, and this flange portion is x2. This is x1, and this is yellow line is xx. So I x1 moment of inertia is this 25 multiplied by 175 cube divided by 12 divided by 12 plus 4375 area for that wave portion, and multiply by distance between this x axis and x1 axis is 129.17 minus 87.5, 41.67, and square of this distance for calculation of moment of inertia. Square of 41.67 plus, now moment of inertia for that flange portion 125 multiplied by 25 cube divided by 12 plus 3125 multiplied by distance between x2 axis and this xx axis. x2 axis is at a distance of 187.5 minus xx axis is 129.17. That means the distance between this x2 axis and xx axis is 58.33. Square. Now calculate this first curly bracket 41.67 square multiplied by 4375 plus 25 multiplied by 175 cube divided by 12 is 18.76 into 10 raised to 6 plus 58.33 square multiplied by 3125 plus 125 multiplied by 25 cube divided by 12, 10.79 into 10 raised to 6. So this moment of inertia is 18.76 plus 10.79, 29.55 into 10 raised to 6. mm raised to 4 is moment of inertia for that T section. Third step is shear stress at top layer of flange is 0. Now shear stress at junction of flange and web. Tau is equal to SAY upon BI. Yes, that means shear force. Shear force for that simply supported beam is S is equal to WL by 2. W is 30, L is 1 by 2. That means shear force is 15 kilonewton. And in this S is equal tau is equal to SAY upon BY. We put this S is in Newton. That means 15 into 10 raised to 3 Newton multiply by area. Area of flange portion is 125 multiplied by 25 because this is junction of web and flange, and above the junction area of flange is 125 multiplied by 25. And y is centroidal distance above this neutral axis. So this y is CG of area above junction with respect to neutral axis. This yellow line is junction, and above junction with respect to this neutral axis, x axis, CG of area. So distance between this bottom extreme fiber to x2 axis distance is 187.5 and minus neutral axis 187.5 minus this neutral axis distance 187.5 minus 129.17, that means 58.33. This distance is 58.33 and this 58.33 is CG of area above junction with respect to neutral axis. And divided by, put this B as it is, multiply by, this I is 29.55 into 10 raised to 6. So 15 into 10 raised to 3 multiply by 125 multiply by 25 multiply by 58.33 divided by 29.55 multiply by 10 raised to 6 is 92.53 upon B. Now shear stress at junction there are two widths. See, between this wave portion and flange portion there are two widths. One width is this 125 mm. One width is this 125 mm and one width is this 25 mm. So calculate for both of these widths. Let us consider B1 is 125 mm and B2 is wave portion width 25 mm. So this tau 1 is equal to 92.53 divided by B1 is 125 mm. So this tau 1 is 0.74 Newton per mm square. And tau 2 is 92.53 upon this B2. B2 is 25. 3.17 Newton per mm square. Now next, shear stress at neutral axis. Same formula, SA y upon BI. S is 15 into 10 raised to 3 Newton. Area is this neutral axis, below neutral axis area, this much area is 129.17 multiplied by 25 mm. And y is this red portion neutral axis 129.17 divided by 2, 64.58, somewhere here from bottom 64.59 divided by B is 25 and I is 29.55 into 10 raised to 6. .24 Newton per mm square is maximum shear stress. Now see shear stress distribution diagram for this T section of simply supported beam. At extreme fiber there is zero shear stress, and at the junction there is shear stress, and at neutral axis also there is shear stress. Maximum shear stress is acts at neutral axis. Here first see this tau 1 0.74 Newton per mm square. This tau 2 3.7 Newton per mm square. This tau at neutral axis is 4.24. Newton per mm square. This is shear stress distribution diagram for the T section. Thank you very much.